Okay, so how is everyone today? Good? Okay. So last time we had just introduced the set of complex numbers. So we had just introduced that. So now we need to talk about the arithmetic of complex numbers. So how about, what if we have two complex numbers, 3 plus 4i, and then we want to add to it, say, 1 plus 8i. So how do you add two complex numbers? You combine like terms in the way that you might expect. You can treat these just like you can treat the I just like an x, so that these are like polynomials. So then what would the real part be after adding them together? 4, because 3 plus 1 is 4, and then what would the imaginary part be? 12. So real part 4, imaginary part 12. Interesting. Besides adding them together, we can multiply them together. So this proceeds with FOIL, exactly, at least at first, exactly how you might expect. So firsts, that'd be 3, and then outsides plus 24i, and then insides, so plus 4i, and then outsides plus 32i squared. So far, so good, right? It's exactly like FOIL. But now here comes a notable difference. What are we going to do with this term? Yeah, I squared is -1. So this would be 3, and then plus adding those together, 28i. And 32i squared, that's actually -32. And then finally combining all the parts together, that would be, what? -29 is the real part, and 28 is the imaginary part. Any question about this? So what happened here, the new thing, is that from here to here, we use that I squared is -1. Any question about that one? Okay. So, what else can you do with complex numbers? How about, let's do 3 plus 4i divided by 1 plus 8i. So now, same two complex numbers as before, but we're going to divide them. So the trick is tonight we're going to take this expression and we're going to multiply by, what's the only thing that we can multiply by and not change the answer? 1. So we're going to multiply by 1. But the real trick is going to be selecting a clever representation of 1. That's going to be the trick. So an example would be something like, we could multiply by 5 over 5. That's 1. Things like this. So this, I hope, you'll get a strong echo of rationalizing denominators. So what are we going to multiply by? 1 minus 8i, and then over 1 minus 8i. So notice that that red bit is equal to 1, because it's the same complex number divided by same complex number. And the reason why we selected 1 minus 8i because it's the conjugate of this denominator. Okay, so now let's carry this out and see what results. That is to say that the numerator should be 3 plus 4i multiplied by 1 minus 8i. And then the denominator will be 1 plus 8i multiplied by 1 minus 8i. Okay, so I'll do the numerator. So that would be 3 minus 24i plus 4i, and then minus 32i squared. The denominator then would be 1 minus 8i plus 8i, and then minus 64i squared. Okay. So we're going to have to do the I squared thing again, which is to say everywhere that we see I squared, we're going to replace it with negative 1. So what will this term become? Positive 32, right? So this would be 3, and then minus 20i, and then plus 32. And look what's going to happen in the denominator. So observe that the 8i's are going to cancel each other. So this is subtract 8i, add 8i, those operations cancel. And then this I squared will also go away. So this will be 1 plus 64. Now, notice that down here, that has no imaginary part. No imaginary part. That was the whole point of making this selection. So selecting this is what caused the imaginary part to go away. That was the whole point. So now that the imaginary part in the denominator goes away, we get the following, that this is 35 minus 20i in the numerator, and in the denominator it is 65. So now, on such exercises, the request is always to give your answer in the form a plus bi. So is it presently in that form? Not quite, right? So how do we get it to be in that form? What do we have to do? Well, we'll do 35 over 65 and this over 65. So 35 over 65 minus 20 over 65 I. And then we can simplify this to something like what? They're both divisible by 5. So this would be 7. And then this would be 13. And then minus 4 over 13. I. Okay, any question about this one? Okay. So complex numbers are so called because, in this case, the adjective complex means consisting of multiple parts. They've got a real part, they've got an imaginary part. The real part for this number is 4, and the imaginary part is 12. So when you want to visualize what's happening, so when we're dealing with just the reals by themselves, the way that we do it to visualize it is we draw a line, right? That works because there's just one number. So real numbers just have one part. So like the real number 7 has just the one part, 7. Whereas when you want to visualize complex numbers, because they have two parts, you have to draw a plane, because there's two different numbers. Okay, so this right here might be the point 7. Okay, so the convention when you're drawing the complex numbers is that this is the real axis, and usually you write a 1 next to it. So this is the real axis. And the vertical one is the imaginary axis. So complex numbers, when drawn, fit on the plane. So if this is the point a plus bi, a complex number, then what's its real part? A. And the reason why it's A is because if you were to go down to the real axis, straight down to it, then you'd measure that to be A on the horizontal copy of the reals. And if you were to go straight to the imaginary axis, you'd measure this to be B. So now, because I drew no scale, you can't tell me the size of A or B, but you can still tell me the sign of A and B. What's the sign of A? Positive. The real part is positive because it's to the right of the origin, the horizontal origin. And B is also positive because it's above the vertical origin. And if I were to ask of you, please plot a point that has positive real part and negative imaginary part, where would you have to plot it? Quadrant 4, which one is that using the words top, bottom, left, right? Bottom right. So, for example, this might be the point, say, 4 minus 3i, because that would be 4 and this negative 3. Okay, good. So let's consider the number 1, and I want you to write each number each in the form a plus bi. Okay. So how about the number 1? Construing 1 to be a complex number. Well, what's its real part? 1. And what's its imaginary part? 0. So this could be written as 1 plus 0i. Okay, similarly, please write I in the same way. So what's its real part? 0. And what's its imaginary part? 1, right? Its coefficient is 1. So 0 plus 1i. Okay, how about negative 1? What's its real part? Not quite. Its real part is negative 1, yeah. And then what's its imaginary part? No. So yeah, 0. How much I does this have? None, right? So its imaginary part is 0. So -1. Well, I specifically am making the request to do this for a reason that's not yet clear. And how about the point -I? So what's its real part? So how much real component does this have? None. Well, it's not clear to me if this is too obvious or too subtle. So let's cover this up for a moment. Consider this number right here, the number of 1, the good old 1. How much imaginary component does it have? None, right? So it doesn't have any imaginary part. And what's its real part? 1. So, as a result, 1 is written as 1 plus 0i. Okay, then I has no real part, so its real part is 0. And then plus 1i. Its imaginary part is 1. So is it clear? Okay. So then how about what is the real part of -I? 0. And then what's the imaginary part? -1. Okay, good. So now what I want you to do is I want you to take all of those numbers, these 4 numbers, and I want you to plot them on the complex axis. So where does 1 go? It's not in a quadrant, really. It's on an axis, right? So it's right here-ish. So that's 1. Okay, where is I? On the vertical axis, right? So right there-ish. So this is I. Where is -1? Very good. And then where is -I? So down here. Okay, that's interesting. So those 4 points, 1i, -1, and -I, there they are on the complex plane. So now, with that context, I'm going to ask a question, a sequence of questions. So we already talked about exponents, so you should be able to tell me what I to exponent 0 is. It's 1, right? Because remember that anything to exponent 0 except 0 is 1. So like 10 to 0, that's 1. Million to 0, that's 1. So this is 1. Okay, how about what's I to exponent 1? I agree, but what I'm looking for is I. It's just I, right? Okay, how about what's I squared? -1. That's straight definition, right? Then how about what's I cubed? -I. It's -I, and let's see why algebraically. Because surely I cubed is equal to I squared times I, right? That's the rules after all, right? X cubed is x squared times x. And then what's this? I squared. That's -1, so the answer is -I. Okay. So far I'd like for you to notice that 1, I, negative 1, negative I, 1, I, negative 1, negative I. So now the next question is what is I to 4? It's going to be 1. Now, why is it going to be 1? An algebraic reason why it's going to be 1. Exactly this, that you could write it as I squared times I squared, because that's how exponents work, and then that's a negative 1, and that's a negative 1, and the product of negative 1s is positive 1. So how about, well, then in that case, what's I to exponent 5? It's going to be I. So now, in case you haven't caught on, so I drew this, I had us draw this for a specific reason. So if you take 1 and you multiply by I, then you get I. And then if you take I and multiply it by I, so that you get I squared, that gives you negative 1. If you multiply by another I, that will take you to negative I. And if you multiply by yet another I, that will take you back to 1. So, observe that if you do I to 4, that is like having gone all the way around the circle, starting at 1, and then you have landed back at 1. So I to 5 is I, either algebraically, because you sit there and think about it in an algebraic fashion, or because if each one of these is a step, and you took 5 steps, where would you be? 1, 2, 3, 4, 5. And furthermore, taking 4 steps is the same as having taken none, right? It's just like a ceiling fan, right? So you can go up to the ceiling fan and click it 4 times. That's the same as having done nothing. If you click it 5 times, that's the same as having clicked it just once to change the fan speed. Okay, well, in that case, what is I to exponent 23? So the question you have to ask is, how many times did you go all the way around? You went around 5 times, and each one of those is the same as having done nothing. Okay, so you went once, twice, 3, 4, 5 times, and here this is I to exponent 20. How much further do we have to go?
3 more.
3 more. So 1, 2, 3. So 23. So what's the answer? Negative I. Okay, how about I to exponent 13, 14? Well, that's a whole bunch of them, isn't it? So, how about the 1,000? Is 1,000 divisible by 4? It is, isn't it? So you could just drop the 1,000. You could just drop it. It's got to be the same as I to exponent 314, because 1,000 is divisible by 4. Okay, how about 300? Is 300 divisible by 4? If you believe. How about 100? Is 100 divisible by 4? Yeah, then so surely is 300, right? So you can drop the hundreds. How about, well, we're already so small, it's not really necessary to drop anymore, I think. So how many times would you go all the way around for exponent 14? You'd go around 3 times. And that would get you to 12. And then how much further would you have to go? 2 more. So then what's the answer? -1. Very good. Any question about this? So complex numbers, we don't talk about them all too much, but we do talk about them a little bit. The last thing I want you to take away from this is that multiplication by complex numbers, this is what it does. It turns things. Okay. So the next section is about quadratic equations. So I could give you a really straightforward one. How about x squared plus 8x plus 12 is equal to 0? And I could say, well, I want you to solve this. Well, this one is really pretty straightforward to solve because this one is straightforward to factor. So does this factor easily? Yeah. How does it factor? So we want two numbers whose product is 12 and whose sum is 8. 6 and 2. So x plus 6 multiplied by x plus 2 is equal to 0. And now this helps us because, have a look. If either of these factors were 0, if either one were 0, then the whole thing would be 0. Right? Because 0 times anything is still going to be 0. So my question to you is how about we ignore the other factor for a moment, all the other stuff, and just ask, what would make that factor 0? If x were -6. So -6 is one of the solutions. And then by analogy, what else must also be a solution? -2. Okay. So any of these kind, this is the simplest possible kind where I give you a quadratic that's monic and also easily factorable. You can do those immediately. The non-monic ones, by the way, what does monic mean? The leading coefficient is 1. The non-monic ones are slightly more entertaining because then you have to do the grouping thing. But you could still do it. So that is to say, if I gave you some polynomial and you got it down to, say, 3w minus 1 multiplied by w plus 5 equal to 0, so it was non-monic, and because there's that 3, then there would be two possibilities for this equation to be true. What's one of the possibilities? So one of the possibilities is that 3w minus 1 is 0. Either that one is 0. And what's the other possibility? Or the other one is 0. So we could solve this equation by itself now. So how do you solve this one? Move the 1 to the other side. This one is pretty straightforward. And then w is a third, or w is -5. So there'd be two answers. Okay, so if I give you one that's monic and factors easily, then you've got it. If I give you one that's not monic, you could still try the factoring by grouping, and then you would have it. But let's take that first example and change it just slightly. X squared plus 8x and then plus 11 is equal to 0. So it's just like the first example, with the exception that we're changing it the constant from 12 to 11. So how about this one? Does this one factor easily? No, it doesn't factor easily, right? So there are no integers whose product is 11 and whose sum is 8. There are no integers that do this. That doesn't mean that there's no numbers that do it. It just means that there's no integers. So our previous method isn't going to work. So today we're going to come up with a method that will work even on this one. But for now it's just a question mark. So in order to get there, let's consider so in the first place, all quadratic equations look like this: ax squared plus bx plus c is equal to 0. So all of them look this way, and we need that a is not 0. We need a to be a non-zero number because, after all, if a were 0, then it wouldn't be a quadratic equation, right? Wouldn't be one. So let's consider the simple case. Let's consider the simple case when a is 1 and b is 0. So then you could reorganize the equation so that it would look like this: x squared is equal to k. So this one is simple enough that we can solve directly with radicals. So we could compute square root of both sides. Square root of x squared is square root of k. And then what's the square root of x squared? Not x. What is it? Absolute value of x is square root of k. Okay, now, supposing that I'm covering up a 5, and we want this equation to be true, what could we put into the absolute value so that a 5 would come out? 5 and negative 5, right? 5 would work, because absolute value of 5 is 5. And negative 5 would also work, because absolute value of negative 5 is also 5. So what are the solutions to this? So one of the possibilities is the square root of k. What's another possibility? Negative square root of k. So we've been able to do this transition for a few weeks now. We've done it a couple times already. But now what I'm saying is that this is a transition that I expect you to make, even skipping the intermediate steps, just beginning to end. So this one to that one. So by way of example, suppose that I give you the quadratic equation x squared minus 10 is equal to 0. So do you observe? So in the first place, it is a quadratic equation. And how much x do we have? Not how much x squared, but how much x? 0, right? So that's what I meant here. So can you make this equation look like that one? Yeah, right? What do you need to do? Move the 10 over. And so what I'm saying now is that from here you should be able to jump directly to the answer. So in the first place, how many solutions will this have? 2. And what are they? Very good. Okay. Any question about, yes?
Would it be okay if I just wrote plus or minus in front of 1?
No. You got to write. So I perfectly understand that some of you have had a previous math class where you write plus or minus we're not going to do this, okay? Because in the end, the reason is that after having had long experience teaching this course now, what I find is that students just don't know how to interpret this properly. So as a result, we're going to strike it from existence in our class. Okay, so what about this one? W squared plus 9 is equal to 0. So now this is a quadratic equation in W. So what's the coefficient for W squared? 1. And what's the coefficient for W? 0, right? How much W is there? There's 0 W. There's 1 W squared. So can you make this one look like that one? Yeah? So W squared is negative 9. And now what notable thing is going to occur now? So we know the square root of 9, yeah, but we're dealing with negative 9 now.
You get the answer is 3i and
Ah, this is what we get, right? Because if we jump to the end now, because now that we have this in the form W squared is k, then the two possibilities are W is negative square root of that thing, or W is square root of that thing. Now, previously, before the last section about complex numbers, the correct response would be to say that, oh, there is no solution. And there is no real solution, but there is a complex solution. So that is to say, we can now turn these into complex numbers. How can we simplify this one? So in the first place, the negative can come out of the radical. And when it does, it comes out as what? How does negative come out of the radical? As I. Right? Okay, then, now, what's the square root of 9? 3. So this would be 3i. Okay, how about the other one? So again, this negative in the radical can come out, and what does it come out as?
negative.
Well, we already have that negative. So ignoring that negative for a moment, this negative comes out, and when it does so, it comes out as I. And then this would be square root 9, and then what's the square root of 9? 3. So W would be negative 3i. Interesting. So we can have complex solutions to such quadratic equations. Okay, so now the trick is that we're going to do is we're going to take an equation like this, and we'll take exactly this one right here. And what we're going to do is we're going to transform it into an equation that looks like that. So if we could make this one somehow look like that one, then we'd be able to solve with radicals. Okay. So that equation was x squared plus 8x plus 11 equal to 0. Okay, so, and I want you to solve it. So since this is the first one of this kind, I'm going to solve it, but I'm going to present it as sort of like a magic trick. Then I'm going to show you how you will then be able to do the trick yourself. So, okay, what I'm going to do is I'm going to take this, and then I'm going to add something to the left-hand side, and it's the only thing that you can add to just one side and it not change the equation. What's the only thing you can add? 0, right? The only thing you can multiply by is 1, because that's the same as doing nothing. The only thing you can add is 0. So I'm going to add 0. But just like when we wanted to divide complex numbers, you had to, in a sense, know the trick of how to select the right form. We have to select the right thing for this one. Okay? So for reasons that I'm not going to reveal just yet, I'm going to say, well, I think it would be really excellent to add 16 and then subtract 16. I'm feeling good about that. That is, after all, 0, right? So now, these first 3 terms, ignore the other ones for a moment. Please observe that those 3 terms factor. How did they factor? So 2 numbers whose product is 16 and whose sum is 8. 4 and 4, right? So these these terms would become x plus 4 all squared. Okay, then we can combine all of the constants together. So negative 16 plus 11, that's negative 5, so minus 5 equal to 0. So these ones became that one. So now I'm going to move the 5 to the other side and obtain the following equation. That x plus 4 squared is 5. And if I cover this up, and if I were to tell you that there's a w in there, then this looks just like the equations that we were solving on the previous page, doesn't it? It's something squared equal to a constant. So that means we can now jump directly nearly directly to the end. So if this said exactly that w squared is 5, then what would the answer be? There'd be 2 possibilities for w. Yeah, w is either negative square root of 5 or w is square root of 5. One or the other. So this is of the form w squared equal to 5. But what's actually in there is an x plus 4, and that makes no difference. So the possibilities are that x plus 4 is negative square root of 5, or x plus 4 is the square root of 5. Those are the possibilities. So now we can move the 4 to the other side and obtain that x is negative 4 minus the square root of 5, or x is negative 4 plus the square root of 5. So when we ask, does this one up here factor easily? The answer is no, because you'd be looking for 2 integers, hopefully, whose product is 11 and whose sum is 8. But if I change the question, can you think of 2 numbers whose product is 11 and whose sum is 8? Sure. Here they are, right? The negation of these. One of the numbers is 4 plus the square root of 5, and the other one is 4 minus the square root of 5, obviously, right? Okay, so I haven't explained at all where I got 16 from. But do you observe that supposing I gave you the trick for you coming up with the 16, then you could do it? Okay. So here's the trick. Let's have another one. How about w squared plus 18w and then minus 7 is equal to 0. So does it, the 2 questions you should ask yourself is, does it factor easily? So does it? No. So you can't do the factoring thing. Okay? Then the next question is, are there 0 w's? So are there 0 of them? No, how many of them are there? There's 18. The reason why we're asking that is because if there were 0 w's, then you could just move the 7 to the other side and be done with it. Okay. So the answer is no in both cases, so now we have to use this new method. So what you do is you do w squared and then plus 18w, and you're going to add something over 2 and square it, and then subtract the same amount. And it's always over 2, and it's always squared. The question is what is it that goes in that numerator? It is this bit. That goes there and there. Okay, so you put the 18 here and the 18 here. Okay, so what's half of 18? 9, and then squared? 81. So what's being suggested is that we should add 81 and also subtract 81. And if you refer back to the previous page for just a moment, you can see that I added 16 and subtracted 16. Why 16? Right, because 4 is half of 8, and then you square it, and that's what you have. Okay, now, these first 3 terms, how do they factor? W plus 9, all squared. So notice that they factor to a square, which is part of the point of doing this, that these become a square. And then we can collect the constants together and get that, and then move the constants to the other side to obtain this. And now this is an equation that's in that form that we know how to deal with radicals. Okay, so then there's 2 possibilities. W plus 9 is, what's one of the possibilities? What is it? Negative square root of 88. And what's the other possibility for w plus 9? Positive square root 88. Then w could be negative 9 minus square root 88, or w could be negative 9 plus the square root of 88. Interesting. So, does anyone know the name of what it is that we're doing here? Because it's so popular and important that it has its own given name. This is called completing the square. So, the first thing that we'll do next time is we'll draw a picture of just why it's called this name, complete the square. Okay, so have a nice Wednesday.